All right. Okay. We're going to look at 3.1 here. So going back to chapter 3, we need to cover regression. Chapter 12 is related to chapter 3, so it just kind of makes sense to hold 3 till the end. So in 3, this first section right here should be pretty similar or familiar to you. We're just doing scatter plots, regression. So why do we study relationships between two variables? We like to be able to make predictions, explain phenomenons, so just try to explain things. What's the difference between an explanatory variable and a response variable? We talked about this a little bit in chapter 4. So an explanatory variable is your one that is explaining. The response variable is the one, the outcome of the study. So the explanatory variable is explaining the response or influencing the response. So if you go ahead and look at this example right here, go ahead and pause the video for a minute or so and figure out which one is the explanatory variable and the response variable. There's Julie and Jim, 2 different scenarios. All right, hopefully you paused momentarily to contemplate this question. If you didn't, here's your chance again. Pause the video and answer it on your own. But here's the answer. So for Julie, the explanatory variable is height. Her response variable is weight. She wants to know if height can predict the weight. Jim, he doesn't care, really. He just wants to know if there's a relationship. So it doesn't matter which one you pick to be the explanatory and which one you pick to be the response. Okay? What's a scatter plot? So a scatter plot just displays the relationship between 2 quantitative variables. Your x variable, if you have an explanatory variable, it goes in the x, explanatory x. And if you have a response, it goes on the y. You don't have to start at 0. Just again, we talked about misleading graphs before, so just be aware that graphs, pay attention to the scale on those graphs, okay? All right, again, here's an example for you. You should all know how to make a scatter plot, so go ahead, pause the video, do the scatter plot on your own. I will show you the scatter plot in a second. Well, this is what it ends up looking like. So here's your scatter plot. Don't forget to label. What 4 characteristics should you consider? So the book gave you an acronym, DOFS. So direction is either positive or negative. The O is for outliers. Again, if you don't feel that you have an outlier, don't worry about mentioning it. Form, right now you're just going to worry about it saying it's either linear or not linear. The strength, strong, moderate, or weak. I'll give you some guidelines when we talk about correlation and how you can decide. Right now, just kind of eyeball it. There's definitely not. It's very subjective. So if I was interpreting the above one, the direction is clearly negative. Maybe this one's an outlier right here. The form, it's fairly linear. The strength, maybe moderate, weak. So there's a weak, negative, linear relationship. Again, if you wanted to say a moderate, that would be fine because it's really not that clear. If you said strong, I might question that. Again, you want to have context there. So there's a weak, negative, linear relationship between sprint time and long jump distance. There may be an outlier. So like I said, there may be an outlier up there. To do this on your calculator, I'm going to put the sprint time and the long jump distance in my 2 lists of my calculator. Whoops. Remember, these are ordered pairs, so they've got to stay together. You can't separate them. So you would go to second y equals, turn your plot on. It's the first graph. Make sure you have your x's. I'm just going to say that the sprint time is the x here. So L1 and L2. Mark is whatever you like. Color, whatever you like. Then you would go to that zoom, use that familiar zoom 9, and there's your scatter plot again. So it's just like what we drew there on the paper. If you trace it, you should get all those points there, okay? So again, you just want to go to that second y equal, just follow these steps right here. All right, if you look at this example right here, you can see just another example of a scatter plot that has 3 distinct clusters. The table gives you McDonald's salads. The variables are sodium and fat. And it says, can you guess which kinds of salads are in each cluster? So you can see that you have a cluster here, a cluster here, and a cluster here. So this cluster here is low on the sodium and low on the fat. And if you think about it, if you look at your choices up here, those are all your ones with no chicken, okay? This cluster right here is high on sodium but low on fat. So these are all your grilled chicken. And this cluster right here is high in sodium, high in fat. So these are all your crispy chicken, okay? So no chicken, grilled, crispy. So again, you can kind of, scatter plots can help us see relationships, help us see patterns. So here I can kind of see a pattern about what kind of salad I'm getting based on those clusters. Does a strong association between 2 variables indicate a cause and effect relationship? So we have talked about this a couple times. So we can only determine cause and effect if we have done a controlled experiment. So if we have randomly assigned a treatment, we can determine cause and effect. So just because there's a strong association does not necessarily mean one is causing the other one. It just means that there is a relationship, okay? So you could say there's maybe a strong relationship, but it's not necessarily mean that one is causing the other one. So those of you that have tuned into the video, let's see if I can quickly find this website here. Sometimes I'm not very quick. Let's see here. Here we are. Okay. Here's some great examples. Now this one is not, these are not necessarily scatter plots. These are often, these are like time line graphs. But anyways, you can kind of see here in this one. So the red one is U.S. spending on, or no, yeah, U.S. spending on science, and the black one is hanging suicides. So they're both trending in the same direction. So it looks like there's a relationship there, but that does not mean one is causing the other one. Here's another interesting one. Number of people who drowned by falling into a pool is correlated with the films Nicolas Cage appeared in. So there's your correlation there. Not super high, but it's pretty high. That last one was very high. So again, but neither one is causing the other one. Per capita cheese consumption correlates with the number of people who died by becoming tangled in their bed sheets. Very high correlation right there. Interesting. Divorce rate in Maine correlates with per capita consumption of margarine. So again, there's a correlation here, but one is not necessarily causing the other one. This is a very interesting website. The guy went on also to write a book, so you can look up more if you would like. All right, so back here to our notes. All right, so what is correlation? So correlation is a mathematical equation that can help us measure direction and strength of a linear relationship. So it is a formula. The formula is down below. And again, it's just giving us the strength and the direction, because it'll give us a positive or negative, of a linear relationship. Like I said, it is a formula. So you can plug numbers into any formula and get an answer, but the result for this particular formula is only good if you're looking at a linear relationship. You can really only determine if you're looking at a linear relationship by looking at a graph, okay? Here's some examples of correlation. So right here, no pattern at all, correlation 0. This one you can kind of see that it's going in that negative direction there. It's not very strong. The stronger the correlation, the more those points are going to fit a line. So this one is just negative 0.3. This one getting a little tighter, closer together, positive direction, 0.5. Tighter here, negative direction, negative 0.7. Tighter here, positive direction, 0.9. Pretty tight here, negative direction, negative 0.99. Okay, the formula for correlation looks like this. You do not have to know it. I'm going to make you use it once here. I think you got to use it once in the homework, but you really don't have to like use it. We'll use it, find it on the calculator going forward. But essentially what's happening is that we're finding the z-scores of the x variable, and then we're finding the z-scores of the y variable. So we're finding the mean of the x, the standard deviation of the x, finding out how far away is each x value from the mean of all the x values in terms of the standard deviations. And we're multiplying those together, adding them all up, and we're kind of taking like an average there, okay? So if the values were all very close to the mean, then we wouldn't see much. If the values were, close to the mean, we would end up with a pretty, if these values were close, this number would be small, so then the correlation would be small. Let's look at the formula. So what I want you to do here, and you can do this on the calculator if you want, I want you to go through, figure out the mean and the standard deviation of the x and the y's. And then I want you, if you want to use the list in the calculators, I want you to find the z-score for the x, the z-score for the y, multiply them together, add them all up, and then use that to divide it by n minus 1. So again, pause the video, do it on your own. Don't wait for me. That would be lazy. I'm not going to help you learn. When you're done, you should get something that looks like this. All right, so then there's some questions down here. So the one question is, what would happen if the x and y variables change? Would the correlation coefficient change? Remember, that's that r. So if I flip these variables, so if I had 2, 3, 4, 5 here, and 1, 2, 3, 4 here, is my correlation going to change? It's not going to change. Nothing's going to happen here, because I'm still going to, these numbers are going to flip spots, but in the end, I'm still going to be multiplying the same thing and adding them all up and dividing them to get the same answer. So if you switch your x and y variables, so in that one we had long, jump, and sprint distance. If we switch which one's in the x, which one is on the y, we're still going to get the same correlation, okay? If the ordered pairs were flipped, so instead of having 1, 2, 3, 4 and 2, 3, 4, 5, if I flip that, what's going to happen here? So then what would happen here, I'd have this negative here with this positive, this negative. So I'd flip, these scores would flip. So then I'd end up with negative correlation, okay? If I multiplied everything by a constant, would the correlation coefficient change? So if I had, let's say I multiplied all these things by 2, would my correlation coefficient change? So if I had instead here 2, 4, 6, and 8, but then my mean's going to get multiplied by 2. My standard deviation is going to also be multiplied by 2 because both the mean and standard deviation are impacted by multiplication. So therefore, in the end, when I calculate those z-scores, everything, the numerator and the denominator both have a constant of 2 being multiplied by them, so they're just going to cancel. So I'm going to end up with the same z-scores. So nothing's going to happen if I transform them by a constant. Does the correlation coefficient have units? So again, when we take that difference in the numerator, divide it by the standard deviation in the denominator, we are canceling out the units. So z-scores don't have units, so there's no units for correlation. And the x and y variables have to be quantitative. If they're not quantitative, then you can't plug anything into the formula to calculate the correlation, okay? Some characteristics here. So it is always, correlation is always between -1 and 1, including -1 and 1. If it's less than 0, it's a negative association. Greater than 0, it's a positive association. If it's close to 0, it's weak. Close to -1 or 1, it's strong. Again, if you want to say, so some kids always want me to give them a rule. So if you want to say if r is greater than or equal to 8.8, you can say it's strong. If r is less than or equal to 0.8, negative 0.8, you can say it's strong. Maybe if you want to say, be between those ones, and you want to classify that as moderate. And then you want to say anything that's, less than I feel like I made these the wrong direction. So less than, so I want to be closer to 0. So anything that's, this one goes this way. So if I am close to 0, then you can say that this is weak. So if you wanted to do it like that, that would be fine, okay? And my brain's not working right now. Yeah, this is right. Okay. You can do it on technology. So again, like I said, you're not going to have to use that formula all the time. So if I wanted to do it on technology, I'd go to stat tests. I would, stat calc. We're going to use option 8. I know you might have used 4 in the past. I'm going to use 8 in this class. You'll know why more tomorrow. L1, L2. Don't worry about the frequency. Don't worry about the stored regression equation right now. I hit calculate. Oh, and I have a slight issue here. All right, so you notice I didn't get my R or R squared. So to get that, you're going to go to second 0. So you get the catalog menu. If you notice here, there's a little A up there that's telling me my alpha lock is on. So I'm going to hit D. And I'm going to go down to diagnostic on. I'm going to press enter. Now if I go to stat calc, option 8, there's my R and R squared. So there's the R for that sprint and long jump problem, okay? So again, there's the answer for the sprint and long jump, which is what I got in the calculator. I usually, if I do these by hand, I usually round them to 3 decimal places. So again, I've already looked at the graph. I know that there's linear relationship, so maybe now I might change what I say. So there's a moderately strong negative linear relationship between sprint time and long jump. Again, if I switch those variables, I'm still going to come up with the same correlation. If we remove this student right here, so the circled one, that pattern is clearly tighter. So then the correlation should become stronger, so more closer to -1. If I remove this guy down here, that point right there is kind of pulling that line down. So if I remove him, there's less of a correlation here between these, so the correlation will become weaker, okay? Can we determine the form of relationship using only the correlation? No, you need to graph. Like I said, you can plug anything, numbers into that formula and get an answer. But if you haven't looked at a graph, you don't know if your relationship's linear or not. Is correlation a resistant measure of strength? No, outliers, like as we can see here, can clearly impact the correlation. All right, go ahead and look at the last example. Pause the video for a second. Read the example. Answer the question. And yes, so the line y equals x would represent equal grades. So the points below the line represent Elaine having lower grades than Peter. So Elaine is consistently harder than Peter because she's consistently giving lower grades. All right, there's your homework for this evening, and I will see you tomorrow.